Well, good afternoon. Have a seat right there and let me give you some lecture notes on Chapter 4, Physical Geography, Weather and Climate. These are the objectives for this chapter. What's the difference between weather and climate? Don't use the words interchangeably. We'll also define various concepts such as insolation, lapse rate, and temperature inversion, and many others. Also, we'll look at some of the controls of temperature and climate, how land and water heat up and cool off differently, how weather works, including the planetary wind and pressure systems, understand how precipitation forms. And hopefully, by doing that, you'll have a better understanding of looking at the weather map on our daily weather report. And also, we'll have a world tour of the climate regions and then finish off looking at the issue of climate change. To start at the beginning, what's the difference between weather and climate? They should not be used interchangeably. Well, weather refers to the state of the atmosphere at any one particular time and place. So you can talk about the weather right now. Look outside and tell me what the weather is like. We can talk about the weather right now. We can talk about the weather we had last night. How cold did it get? Or we can also talk about the weather in the future. What do you think the weather is going to be like on the Sunday church picnic? So weather is the state of the atmosphere at any one particular time and place. Climate is sometimes vulgarly defined as being average weather, meaning the average conditions of temperature, the average precipitation totals, and so forth. So weather in the aggregate, perhaps? All right, but climate is more than just averages because climate also includes the extremes and the variation from normal. All right, we'll take a look at some examples of that. And also, it's probably a good time to define what meteorology is. Meteorology is the study of weather. So a meteorologist on television would be answering questions like, is it going to rain today? How cold is it going to get tonight? Is it going to snow? And how many inches of snow are we going to get? Now that's a little bit different than climatology. Climatology is the study of climates. Well, what climate questions might you have for a climatologist? Well, you might ask them, well, I'm planning on going vacation in a particular area, say a particular state, and a particular time of year, and you want to ask them, what's the atmosphere like at that time in that place on average? So you can plan your vacation out using climatology. Climatology comes up a lot in agriculture. While it might be a meteorology question to ask something like, is it going to rain today? A climatology question might be, does it rain enough to grow corn in this environment? You see, in the United States, if you've ever made that transect from east to west across the country, you probably notice that it gets drier and drier as you go further west. At some point, you drive over a line where it's too dry to grow corn anymore, and they have to think of some other crop. So climatology is important. It's important in agriculture, in engineering, how buildings are designed, and so forth. All right, so meteorology, that's the study of weather, and climatology, that's the study of climate. Now, there is one other big question for climatologists, however, and that's the idea of climate change. And it seems like a basic question. Uh, are our temperatures getting warmer? And we'll take a look at that at the end of this chapter. Okay, just to make sure that you have a handle on the difference between weather and climate, look at this list of statements. They all have something to do with Ohio, in case you didn't see that. But let's see. So there is one statement that refers to both. Okay, so if you said something like the Guardians baseball game was rained out today, then that would be weather. If you said the high this afternoon got up to 29 degrees Celsius in Dayton, that would also be weather. You're talking about the state of the atmosphere at a particular time and place. How about this one? Last evening, a tornado ripped through Canton. Well, that's the state of the atmosphere at a given time and place. But how about this one? January is usually Cincinnati's coldest month. All right, that's climate. That's the usual, or that's the expected. All right, how about this one? The weatherman said that it's partly cloudy in Toledo. That's weather. How about the coldest temperature ever recorded in Kent was minus 19 degrees Fahrenheit? Well, that one might be a little bit of weather and a little bit of climate. I'm leaning more towards it's more of a climatological statement because it's giving you a measure of what can happen in that environment. All right, and then Chardon is the snowiest town in the state. That would be climate. That's up in northeastern Ohio, up in Amish country. It gets very snowy up there with the lake effect snow. All right, so I get the idea that you're sitting there and you understand the difference between weather and climate, and you're not going to misuse those terms. Okay, how about hurricanes? Are they weather or climate? Well, it depends on the context of your statement. Certainly here in the southeastern United States, hurricanes are an important part of our climate. And if a hurricane arrives, it brings very windy and very wet weather to us. So with climatology, the study of variations from normal and what extremes can happen are an important part of the assessment. And speaking of extremes, here's another hurricane image, Hurricane Katrina. So again, if you live in the southeastern United States, they're an important part of the climate. Moving on to the next topic, let's take a look at what the atmosphere is. Now, the atmosphere is a very thin layer of gases surrounding Earth. Now, if you were to compare an Earth diameter of 7,900 miles, how thick is the atmosphere in comparison? Well, you have 99% of the atmosphere is within about a dozen miles of the Earth's surface. So that's a very thin veneer around planet Earth if you compare 12 to 7,900. Now, atmospheric scientists divide the atmosphere up into layers, and most of this is beyond Geography 1010. We live in the lowermost layer, that's the troposphere. Above that is the stratosphere, where our ozone layer is. And above that is the mesosphere, where most meteors burn up. And then above that is the thermosphere, where you have the electrical charged particles of the auroras up there. All right, as far as atmospheric composition goes, 78% of the gases in our atmosphere are nitrogen. All right, only 21% oxygen, and the other 1%, there are some gases like argon, a little bit of helium. But importantly, there are some trace gases, there are some greenhouse gases that are very important in keeping and regulating the temperature of the lower atmosphere. Okay, now the one graph that I have on here. This is a graph of pressure, and this shows that the atmosphere gets thinner and thinner as you go up towards outer space. We haven't talked about pressure yet. That will be for a later slide. But we can talk about right now is the pressure of the atmosphere is the density of the air or the overlying weight of the air. When you get up to about 12 miles up, you can see that, looking at the area under the curve, you're over the vast majority of it. And it's just the air is thinner and thinner and thinner as you go up. Sometimes kids ask the question, where's the dividing line between our atmosphere and outer space? Well, there really is no definitive line. It's just that you have fewer and fewer air molecules as you go up. Some have defined an arbitrary line, but that's arbitrary. An important term that you need to know about is the word troposphere. The troposphere refers to that lowermost layer of our atmosphere. Now, atmospheric scientists divide the atmospheric layers based on their temperature characteristics. In the case of the troposphere, almost all of our weather occurs in this what we call the lower atmosphere or the troposphere. The word tropos comes from the Greek, meaning to turn, to churn. So the air is always mixing there. All the storms and so forth, that occurs in the lowermost layer of this troposphere. Also, something about the troposphere, as we'll see later, overall temperature declines with height throughout the troposphere. Now, above the troposphere, there's another layer called the stratosphere, and that's where our ozone layer is. But that topic will not come up until we get to chapter 12 on human impact on environment. Here's a question. What is it that most directly warms the Earth's lower atmosphere? Well, I know what you're going to say. You're going to say, well, the sun warms the Earth's atmosphere, correct? And, well, while it might be that the sun is the ultimate source of energy, it's not the one that most directly heats the Earth's troposphere. You see, the way that it works is this. The sun warms the Earth's surface, and then the Earth's surface gets warm and radiates its heat, and that's absorbed by the gases in our lower atmosphere. So it's not the sun warms the atmosphere directly. The sun warms the ground, and then the ground warms the atmosphere. And for this graph, I'd like you to look at, first I'd like you to tell me what's the relationship being shown on this graph. Whenever you're reading a graph, always make sure you read and understand the axes first, and then the rest of it is easy. Okay, let's not look at anything that's above the tropopause. Let's just look at what's going on within the troposphere. All right, so we have temperature on this axis, low numbers to high numbers, and altitude on this axis, low numbers to high numbers. It's ticked off in kilometers here, but you have miles and even feet are ticked off over here as references for us Americans. Well, what's the relationship between temperature and altitude? Okay, you have a temperature decline with height. As for every unit you go up in height, you pull down on the temperature axis. So it's a temperature decline with height of around 6.5 degrees Celsius per kilometer, or 3.5 degrees Fahrenheit for 1,000 feet. Temperature declines with height. But would you expect that? Why does it get colder as you go up. The ancient Greek philosophers couldn't understand why you had snow-capped peaks. Doesn't it get hotter as you go up into the sky? You're going closer to the flaming chariot that goes across the sky every day. Aren't you getting warmer as you go up? But remember, the sun isn't the direct heater of the lower atmosphere. The atmosphere is transparent to sunshine. Sunshine strikes the ground, and the Earth's surface warms up and radiates heat radiation, long wave radiation that's invisible. And our gases in our atmosphere are very good at absorbing that heat radiation. So as you get away from the surface of the Earth, this is especially notable if you ever take a hot air balloon ride. It gets colder and colder as you go up in altitude. All right, and also the thinness of the atmosphere too. There's less mass, there's less air molecules the higher you go up to even absorb the radiant energy of Earth. So for those reasons, you have a temperature decline with height in the troposphere. That's the average lapsing off of temperature. This lapse rate is around 6.5 degrees Celsius per kilometer. All right, so our atmosphere is mostly warmed from below. Yes, and for this diagram, what heats the atmosphere. All right, so a few terms here. What's insolation? Notice I didn't say insulation. Right, that's that pink fiber stuff that you have in your attic. Insolation, it's a contraction of incoming solar radiation, otherwise known as sunshine. All right. Well, looking at this graph and the proportions on the graph, you see this top part here, solar radiation entering the Earth's atmosphere. Okay, if this yellow here, if that's 100 units, what happens to it? Well, you lose about 32% right off the bat due to reflection. Either backscatter of the air molecules themselves. Clouds are very good reflectors. White clouds reflect a lot of solar radiation. And the ground surface can also reflect sunshine as well. The snow and ice fields, sandy beaches are good reflectors. All in total, the reflectivity, there's a term for that. The total reflection of the Earth system is about 32%. The term for that is albedo. All right, so you lose that right off the bat. Well, then what about all this over here? What happens to it? Well, you had to go to college to learn this, but for the most part, the Earth's atmosphere is transparent. See that 50 there? That's the biggest, widest portion of that's not being reflected. All right, now there is some absorption by dust in the atmosphere and air molecules, and water vapor is very good at absorbing the near infrared of the sun. Some is absorbed by clouds, but for the most part, sunshine zips right through the atmosphere and strikes the surface of the Earth. Okay, well, how about reflection? Well, reflection, that's when the sunshine bounces back. That's not being used to heat anything. Okay, this sunshine reflected off the clouds, that's not heating the clouds. See, the lower atmosphere is warmed by, now my spell checker says this isn't a word, so I had to put a hyphen in there, re-radiation, because the sun warms the ground, and then the ground heats up and re-radiates, or it'd probably be better to say then the Earth radiates heat radiation, long wave radiation, that the gases in our atmosphere are good at absorbing. All right, so reflection is not what heats the lower atmosphere. Lower atmosphere is warmed by the re-radiation of the Earth's surface. Okay, continuing. So you learn that why I might say that the atmosphere is transparent. And for the most part, the atmosphere is warmed from below. Something else that transfers heat in the atmosphere is convection. That warm air rises and transfers heat. Well, warm air rises and cold air sinks. That'll be an important concept as we move forward. And also an important part of the story about why we have a warm lower atmosphere is the role of greenhouse gases. Now, greenhouse gases include water vapor, carbon dioxide, methane, O3 molecule, ozone, and oxides of nitrogen. These gases are very good at absorbing the long wave heat radiation of Earth's surface. Especially the one of concern is carbon dioxide. It's a very important greenhouse gas. Carbon dioxide is given off by burning fossil fuels or by burning practically anything, by respiration. All right, so carbon dioxide is very good at absorbing the Earth's long-wave radiation. So the issue with global warming and climate change is that the excess carbon dioxide we're putting in our atmosphere is retaining more long-wave heat radiation of the Earth than we should, and that's an issue. Now, the greenhouse effect is a completely natural effect. That's what warms our lower atmosphere. And actually, water vapor is the most important gas on all of that. But the other ones, methane, nitrogen oxide, and ozone, they're also greenhouse gases. If it wasn't for the greenhouse gases, we wouldn't have a livable lower atmosphere. All right, so the sunshine goes right through our atmosphere. What about carbon dioxide? Well, sunshine goes right by carbon dioxide. Carbon dioxide doesn't care. But sunshine then warms the surface of the Earth, radiates long-wave radiation. Carbon dioxide is very good at catching that long-wave or heat radiation of Earth's surface. For those of you that are going to be teachers, or if you just want to have a better understanding of it, I sometimes use this example for how important greenhouse gases are, even though they're only a small percentage of all the gases in our atmosphere. All right, first I want to have you imagine a 10,000 seat basketball arena. All right, so 10,000, that's a nice round number. All right, now nitrogen is 78% of the atmosphere. So the 7,800 seats are filled with fans of the home team, Team Nitrogen. And they're sitting there, they're cheering, okay? And the visiting team is Team Oxygen. And they're filling up 2,100 seats. Now let me ask you this. In that 10,000 seat basketball arena, do the fans influence the score of the game? Well, I suppose they're cheering for their home team, and you might have home team advantage and so forth, but it's not the fans that are putting the ball in the basket. So much like nitrogen and oxygen, they're not really influencing the score of the game. What's the score of the game? Well, if the score means the atmosphere temperature, because sunshine goes right by nitrogen. Most of our atmosphere is nitrogen. However, you have the players. All right, so the greenhouse gases are the combined number of players. All right, how many players do you have? So you have 25 on a team, plus you have your coaches and assistants and so forth. So you have the two teams together. That's only a few dozen, right? In out of 10,000. So that seems like that's a very low percentage. But the thing is, it's the players that determine the score. How many of them you have in the arena will influence, all right, what the score or the temperature is. All right, so it's not the 10,000 screaming fans that are influencing the score. It's the 50 players that are determining the score, and the same with our atmosphere. You know, it's not the 99 and greater percent of our atmosphere that's determining the temperature. It's that small percentage of greenhouse gases in our atmosphere that are absorbing the earth heat and thus regulating the temperature.